well, binary trees, not just trees, but specifically binary trees. And so for speakers, we have Kajari, myself, my name's Amy, and we have Juella. And so we're going to review sort of the applications of trees and what they're used for, why they're useful, vocabulary around trees. So what are some of the terms you might hear if someone asks you a binary search tree question, you know, like height, things like that. So we'll cover that. The structure of a tree, the difference between trees and binary search trees. So what is specific about binary search trees that makes them unique? Talking about unbalanced versus balanced trees, and then we're going to talk about the complexity of the trees. So Juella, I think that's you.
Oh yes, yeah.
Oh wait, one thing, Amy, do you want to present this? It's like up on the right.
Oh, am I not presenting it?
No,
oh.
You're like manually clicking through.
Yeah, I think. Okay, let me try that. Yeah. Let's see.
Yeah. Perfect.
Okay, cool. Awesome. Thanks.
Okay. Yeah. So here, it would be great if you guys have any questions about anything, and please stop us if you guys have any questions. And also for all the people in the watching the YouTube live, post it on the comments, and we're going to try and answer your questions as soon as possible. All right. So, well, first, I just thought that it would be really great if you just to understand the applications of why it's important to for trees, right? And if you can go to the next slide, Amy.
Yes.
So, all right. And if you can go, okay. So this is just example applications that are that. If you can go to the next slide, Amy. Mm-hmm. All right. So these are just sample applications. First, I want to talk about like how sort of like when you look at the file system, how if you look at it, it kind of looks like a tree, and it's stored in a hierarchical way, right? And you have tries that's also stored like a tree, and network routing algorithms. So that source, you can watch it over here at youtube.com, and you can get more information about those type of applications. If you can go to the next slide. All right. So for instance, like this, if you have a Windows operating system, if you go to your, let's just say like Explorer or something, and you just look at, I just took a screenshot, and it's just the file system structure is just an easier way, if you use easier way to for trees, right? So like you can see it here. So like the computer is the root, and then under that the child of the computer is local disk. So it's just an abstract way of looking at what a file system structure is without really looking at what the underlying hood, right? If you go to the next slide. Mm-hmm. Which is actually like, it's a nice visualization of the file system structure, but it's not really how it's implemented in the Unix file structure system. So I wanted to know more like, how is it actually implemented? Like, are they kidding? Are they joking with us? Like, is it that simple? And actually, when you're trying to, let's say, if you want to make your own Unix file structure system, is it like just making a tree, right? If you go to the next slide.
Oh, and by the way, that has come up in interviews where they'll ask you to model a file system. So this is important.
Yeah, but if you actually like do it, like how these kernel developers write their Unix file structure system, it's kind of different from like the trees. This tree sort of like simplifies it. So this is, if you read this more, it uses inodes, and it's also its own complicated data structure. And you can find out more about that if you just Google it. But I thought it was interesting. Like the file structure system, it's more intuitive if you see it as like a tree, but internally it's not that simple. So just wanted to point that out. And then if you go to the next slide. Okay, so a sample one, for instance, is a B trees, and it's a generalized binary tree, and we're going to be talking about that later on. And what this is just it performs a logarithmic runtime on operations such as read, delete, and search. And this is actually widely used in databases. Like SQLite 3 uses B trees to to load things in external memory. So, right. And that's all I have for applications. And now I'm gonna give it to Kajari, and she's gonna talk about the vocabulary of trees.
Okay. Yeah, so one thing to note about trees is that they're a type of graph. And there's a graph on the left and a tree on the right. And so all trees are graphs, but not all graphs are trees. It's just something to keep in mind, right? Okay, if we can go to the next slide. Yeah, okay, so these are like kind of the vocabulary. There's a parent. Okay, well, let's go to the next slide. It has a better picture that we can use. Okay, so here's a tree, and the topmost node is called, okay, so each of the points are called nodes, and the connections are called edges. So something defining about a tree is that each node can only have one parent, and that's what makes it different from a graph, because in a graph, a node can have several parents or like several nodes leading into it. But with a tree, only one node will lead to it. So, okay, so here are the terms. The first parent node is called the root. Anything that it leads to is a child, and they can be referred to as children. So like node 2 over there, its parent is node 1. And its child is node 4, node 5, and node 6. And node 4 and node 5 have the same parent, and so node 4 and node 5 are siblings. Okay, so then if you look down at the lowest level, if you have a node that has no child, it's called a leaf. And so these are just some terms to keep in mind. And it kind of makes sense, right? Like, you know, I have only one mom. But yeah, so, well, biological mom, yeah. So that's my parent, and then I have siblings, and they're on the same level. Okay, so if we go on to the next slide. Okay, yeah, so these are just the characteristics of trees, and I've just written them out here, that each node must only have one parent, and edges only go in one direction, as opposed to a graph where they might be bidirectional. Okay, and then if we go on to the next slide. Okay, and these are some things to know about trees. If a tree has n nodes, then it will always have n minus 1 edges. And you can go and like find out the mathematical derivation of it. We're not going to go into that because we don't have that much time here, and it's more of a review here. And then the depth of a node is the number of edges from the root node to that node. So if we go back a slide, on another slide. So here, like the depth of node 11, or the depth of the tree will be 1, 2, 3, 4. 1, 2, 3. Sorry, that's the height. Sorry. The depth of node 11 will be 3. The depth of node 3 is 1. The depth of node 8 is 2. Okay, so if you go forward 2 slides. Oh, no, back one. Yes, sorry. And then the height of the tree is basically the deepest node. It is the number of edges between the deepest node and the root. So in the graph that we were looking at before, the height of the tree was 3. Okay, so those are just some general terms to know. All right, and so next slide. Okay, a binary tree is a tree that has at max, like a node of a binary tree can have maximum 2 children. It can have 0 children up to 2 children. And something to note is, unless you clarify with an interviewer, they're most probably talking about a binary tree. But so, you know, when they say tree, it's just like clarify. All right, okay. Then binary search tree. So an application for using trees is to store data and to make it very easily searchable. So the difference between a binary tree and a binary search tree is that the value of the left child must always be less than the parent node, and the values of the right child, the value of the right child must always be greater than the parent's value. So if we go to the next slide, we have a picture of the, yeah. So on the left, you have a binary search tree. So you'll see that every node on the left of a node is smaller than that node's value. So 1 is smaller than 2. 2 is smaller than 6. But all the right children are greater than the parent's value. So 8 is greater than 6. 4 is greater than 2. And as opposed to the tree on the right, where that is a binary tree because each node has at maximum 2 children, but the value of the left child is not always smaller than the parent value, and vice versa.
Okay, great. So I'm going to talk about unbalanced versus balanced trees. So when you insert something into a tree, I think, so you can see in this picture, it needs to, you know, as Kajari mentioned, it needs to go into the proper spot based on its value. So binary search trees have values that are less on the left and values that are greater on the right. So what can happen is you can keep inserting things into a binary tree, and you could keep adding it to one side just because values, you know, happen to be greater. So a tree can become unbalanced, and that basically affects how efficient it is to search through that tree, and basically affects the efficiency and the purpose of the tree. So tomorrow in our algorithms meetup, like our in-person meetup, we're going to be going through some problems, and I believe one of them is about how to balance a tree and what the implications of unbalanced trees are. So this is kind of our review of binary trees before we get into those problems tomorrow. But anyway, so you can see on the left side there's a non-balanced tree, because values kept getting added and they were all greater than the root that happened to be one that began the tree. When you balance a tree, you can see on the right side the height of the left subtree minus the height of the right subtree is 0. And that goes recursively for every smaller subtree. And if there's any imbalance, that balance factor could be -1 or it could be 1 or greater. You know, like in the left case, it's, well, I guess, yeah, in the left case it's greater than 1 because the height, as we talked about, is, you know, a greater than 1. So the way that you balance a tree, so it's a pretty complex, it's a time-consuming, resource-consuming process to rotate a tree to get it balanced, but this is a really simple rotation with 3 values, with 3 nodes, and you can see that the way that you rotate it is the middle value becomes the new root, and nodes A and C become the left and right children of that parent node. But if your tree is a lot more complex, that rotation, you need to do it recursively, and you need to check that it's balanced, and you might have to do it several times. There's really good links on rotations, and I know in interviews I've had to not code rotations, but at least talk about how to do them in theory, so it's helpful to go over it. And we can talk about it more tomorrow if needed. Let's see. Can one of you talk about traversals?
Yes, that's my.
Okay, cool.
So traversals is just a way to basically go through a tree and print out or visit it or do whatever operations that you need be. And so for the pre-order, I guess if you look at my. Okay, so sorry about that. So pre-order is just.
Hey Kajari, before you get into traversals, there was a question that was asked by Jaren, and I'm going to go back. Is that okay? Can I jump in and answer the question, and then we can go into it?
Yeah, and actually, Juella is presenting on traversals. And Juella, if you want to show your screen, go to the left side and share your screen so we can see your tablet or whatever you're drawing on. Okay. Okay.
Yeah, give me 1 second though. I'm going to go back to a question. So the question was, why is the tree on the right not a binary tree? The only difference is that 7 node, and it's greater than 4, so it should be on the right of 4.
So can we go back to that slide?
I'm on that slide. This is the slide, right?
Oh,
Yeah.
sorry, hold on. I've looked away from the.
I mean, I can go over it really
Yeah,
quickly.
can you go over it? Sorry.
Is it on the screen right now? Can you see the one that's a binary tree on the left and not a binary tree on the right?
Oh, there we go. Yes.
You got it? Okay, cool.
Yeah.
So the reason that that one is not a binary tree is because the way that you insert things into a binary tree is by looking at the parent. So your traversals will always start at the root node, and 7 is greater than 6, so you automatically need to be going to the right side of that tree, and because it's less than 8, it should then land into the left side of that 8 node, and that's why this isn't a binary tree, because it's in the wrong position even though it's greater than 4. And the reason that it needs, I'm going to get into this later, but the reason that affects it is because the search time for binary search trees are log n, meaning like you can divide the tree into half at every point and say like, oh, okay, so it's going to be less than that, I'm going to go to the left. It's going to be less than that, I'm going to keep going to the left. But that 7 throws that off because I'm going to be going to the left expecting something little, but that 7 is actually greater than the root. Does that make? Hopefully that makes sense. Kajari, does that make sense?
Right.
Okay.
Yeah,
okay,
and
cool.
so the beauty of a binary search tree is that all of the nodes to the left will be smaller than that node, and all the nodes to the right will be larger than that node, the values. So exactly as Amy explained, this because the 7 is on the left side of 6, even though it's like in a subtree, it throws off the binary search tree characteristic.
Cool. Okay, I'm going to go back to traversals. Okay. Oh, and you're trying to share your screen, is that right?
Joella?
Yeah, I'm so sorry about that. I keep getting booted out in my network. I don't know why. I feel like someone's streaming Netflix here or something. So I'm so sorry about that, guys. Okay. Did someone like take over or so, or?
No, we're just starting traversals.
Okay.
Did you want to share your screen with your tablet, or?
Yeah.
Okay.
All right. So, I wanted to, if you go over like my, I guess.
Amy, click on Joella's.
I did.
Oh, okay.
I did. It's a little laggy. It'll get there.
Oh, okay.
Okay. All right. So I wanted to talk about go over what I mean. I don't know if many of you are. I don't know. To be honest, recursion to me is not intuitive. It seems I feel like I don't know. For me, when starting out with programming, it wasn't.
We can't hear you anymore.
I think we lost Joella. Okay, we can come back to traversals and we can keep going. Is that okay?
Yeah, it's fine.
Okay. Let me go back to this, present it. How did I? Oh, right here. You can see it now?
Yep.
Okay, cool. I think this is okay to cover this because I just talked about sort of the complexity. But so when you're trying to add something to a binary search tree, the fact that it's balanced, like I said before, makes it really easy to add a new node to it. So you know exactly how to traverse it. And not only balance, the fact that it's a binary search tree and the fact that it's balanced, you know how many levels you're going to have to go to add that new node onto it. And you can see down here, this is a fairly simple insertion because you're adding a leaf node to it, and you're adding the 19. And if you traverse through the tree, the 19 goes to the left of the 29 just based on the properties of a binary search tree. If it's not balanced, as we saw in the really long the long noded tree, that's O of n. So that's the worst case of a non-balanced tree is O of n, obviously, because it's all one-sided and like left heavy or right heavy, and that's what the complexity is going to be. But for a balanced tree, it's O log n. And same thing with subtraction. at the point of subtracting it, if you keep the balance the way it should be, it's also O log n. So you can see here that the 25 is being deleted. So the 35, that parent node comes up to the next level, and I think after that, this tree will need to be balanced. So that balancing adds another thing that you need to do every time you detect that your tree is unbalanced. So once that 25 comes out, the level difference will be greater than 1, and you will have to balance the tree. This one is a more complex subtraction. And I think one of the problems tomorrow might be on adding or subtracting nodes. I can't remember. But anyway, this is a more complex subtraction because you see that the 5 goes away, but the successor of that node is the smallest value on the left subtree of that tree, and so that becomes that node. It becomes the next. It becomes the parent node of that subtree, and I believe then this one, yeah, it also. Does that need to be balanced? No, I think it looks. Oh, yes, it does. Yeah. So. Actually, no, that one looks okay. But anyway, so yeah, so these are subtracting. In searches, they're sort of, so searches are similar to adding and subtracting, except you're not manipulating the values, you're just looking for them. And the reason that binary search trees are so great is because the searches are log n. Okay. Joella back. Joella, are you there? No, Joella? Well, I guess maybe her mic isn't working.
Oh, what the
Okay. Joella, are you there? Or I can hear someone's mic not muted. That might be.
Oh, Amy?
Mm-hmm.
Joella's on the phone with me, and she's just
Okay.
going to use my mic to talk.
Cool. That works.
Okay, perfect. Okay, so Joella, you're on.
Okay, can you guys hear me?
Yes.
Wait, did you hear her? Oh, wait, Amy.
Yes, we can hear.
My headphones on so she
Okay,
can hear you.
Yes.
Okay, so
Alright.
Joella,
Just a
talk.
minute.
Somebody from there respond.
Alright, just a bit irritating. I don't know what's wrong with my network. I think that it can't handle like to Google Hangouts or something like that. So I'm sorry about this, guys. So I want to talk about just briefly about like what happens inwardly when you do a recursion call on like pre-order, right? And can you guys see I'm on my tablet right now, so I just want to like indicate like how pre-order works.
Mm-hmm.
Can you guys see it?
Yes, they can see it.
And for those of you that are on the live Hangout, click on Joella's tab so that you can see as Joella does it, because I think the main stream has a little lag.
Okay. Is everyone on my screen screen sharing with me?
Yes. Can you?
Yeah.
Yes? Okay, good. All right, so I'm just going to go ahead and sort of present like what a tree, if you have like a simple tree, right, and what a pre-order looks like. So you have this structure node, or it would be like a class in Java. So you'd have like a data D that stores like string or integer or whatever, and a pointer to the left and a pointer to the right, right? And then for pre-order, it's pretty simple. It has a space case where you're asking to see if like making sure that R is not null. So because like you can't like operate something on null, right? And then you visit D, or like you either like print it out or you store it somewhere. You just visit, right? And then you go through the left subtree, so right here. So you go through the root, and then it visits this part, right? And then it visits these sub. Actually, sorry, it's going to be R, not T. Okay. So R's R's right subtree, which is in this case here. Okay. Okay. So now that I want to go through like, okay, so what happens when you like visit A's left and you know, A's right. So not sure if I'm just gonna assume that some of you don't really know what a callstack is, and so what a callstack is basically it's just an abstraction of what happens under the hood when you basically load the program in your computer, and then it goes through each instructions, right? So and what happens with that, right? So in here, I'm just going to. Okay, so here what happens is that when you pass in a pointer of A, which is the root, okay, and then it checks to see. So in here, so you have pre-order A, right? And then it checks to see. Okay, so A is not null, so it's going to visit it. So here we're going to say just print it out. So we're going to print out A, okay, and then it goes through B. So it goes through this instruction right here, which is A's left pre-order B. And afterwards, it's going to visit here. So it goes here, and then it visits D, right? So we have B here. And then it visits this, and then it goes through B's left, which is G, right? And then afterwards, it visits G's left again. It's right here after we print it out. Okay. Now this one is sort of like it kind of ends here because when you try to visit I's left, it's going to return. So it's going to have so just say okay. So you're essentially like say pre-order now, right? But this is not, so you can't do anything with it. So it returns. So this one it exits it out, right? And then afterwards you call I's right, which is null again, so it returns, so nothing really happens. And so you're done with I. So because you just called like I's right here. That ends here. And then afterwards so since you remember last time we said G, like pre-order G's left, right? And which is I, and that was done. And now we're gonna go through G's right, which is H. And then, so after sitting G's right, we then we print it out each here. Okay. Now, as you remember, H doesn't have right and a left child, and so this one, when we do these calls right here, it returns. So essentially, it's going to finish up H. Okay. And afterwards, so you're pretty much done with this subtree right here, and so you're going to go back to your to this one right here, right? So you're done with this. So you go through pre-order B, right? And then remember, G was the left subtree, right? And now the right subtree is D, right? Or it's a leaf. But let's just say that we don't know like what B's right subtree is. So we're going to call pre-order. Right. And here you have what? So you call D, right? And it's not null, so you're going to visit it, or in this case, you're going to put it out, right? Okay. And then afterwards, you're going to call D's left, which is null, so it returns. Okay, and then you're going to call D's right again, but it returns because it's null, right? So you're basically done with D. And now you have returned to in this case, right? So you've done this, which is this is D. So this is done. Okay. So this ends. And now you went to the root, which is A. And then you're going to visit A's right subtree. Because remember, when we said A, right here, visit A, and then visit A sub tree, which is this right here, and then afterwards you finish this call right here, and now you're going to go to this instruction, which is pre-order R.write, which is C, like C's, I guess, sub tree, okay? Okay, so C is not null, right? So you're going to visit it, so you're going to print it out. And then you're going to call C's left, right, which is E, okay? Right. Afterwards, you're going to call, okay, so here E's not null, so you're going to print it out. And then afterwards, you're going to call E's left, but that's null. And E's right is null. So essentially, this ends the instruction right here. It's function call, yes. And so with C, now you're going to call, so remember, this was C right here, right? So we had C here, and this was E right here. So C's left, which is E. And now we're going to visit F. Right? So C's right. Okay. And so F's not null, and so we're going to visit it and we're going to print it out. And basically, this is how, okay, after visiting F, now F's left is null and F's right is null. And so essentially this ends the function called F, right? And then afterwards, well, you're done with C's right because you return. Right? So this one exits it out. And then now you've essentially returned to when you call pre-order A, and now you're done, basically. And which is why it's super important. So this is the result of pre-order traversal, right? And this is why it's so important to have a base case on every recursion, because if you don't, you're either going to have like two ways. Like if you have like really deep trees, right? Like you're either going to run out of memory in the stack, or you're going to have a null pointer exception because it's going to realize you've like essentially like you're going to, that's just for simplicity's sake, you like pass in I's like left, right, which is null, and it tries to visit or tries to print it out or do some instruction. So it says like reorder null dot left, so it's going to give you a null pointer exception. So yeah, I mean, I don't know, like I felt like in the beginning as like a programmer, I kind of didn't understand so much of like, oh, you have like these errors, and it was kind of not intuitive. But then finding like going through like what the stack calls are, like just going through this abstraction, it really helps. So I hope that that gives some I guess it helps right with explaining and sort of going through like what recursion really is. And so that kind of took long, but if Amy can go through the next slide, I just wanted to show sort of like the code for it, and it's actually like pretty simple. So.
Yeah, give me 1 second.
Amy?
Yeah, 1 second.
Amy's saying 1 second, just in case.
Okay, sorry.
Yeah.
I can't hear her.
Okay, it should be up now.
Okay, awesome. So this is basically what the code is. So you just like you visit R's subtree, and then you visit R subtree, and then you print it out or do something with it. And then if you go to the next one, the same. That's supposed to be in order, not post order. Sorry about that. And yeah, so it's basically the code for it. It's, I don't know, I guess you just have to memorize the in order, post order, and pre-order for that. So like memorize it with like different mnemonics. But I know that with interviews they do ask about like, visit traverse a tree, or do it optimally and stuff. So yeah.
Yeah, and it would have made more sense for the searching and adding, because so basically traversals are important in order to add, search, delete, and even balance trees. So the way that like the type of traversal you pick is going to impact it, and when you're adding something to a tree, how you traverse it is, that's what that traversal stuff is about, like how you're adding, how you're searching for stuff. Yeah. So I think that's all the slides we have to cover.
Yeah. If anyone has any questions.
Yeah, I think it's going to be difficult to do questions over this, but I know that we've gotten questions through the YouTube video, through the email, like the public email, and also on Slack. So I'm assuming everyone who's watching this is probably on Slack, but if you go to bit.ly/womenwhocodec Slack and sign up, we can answer questions there too. Are we good?
Yeah.
Yeah, I don't have anything more. Oh, also tomorrow is our algorithms meetup. We are going to be doing problems that are related to binary search trees, and if there's any questions you have, you can ask us in person. We'll be there. So see you all tomorrow, hopefully.
Yep.
Cool. All right.
Come with questions and, come ready to do some algorithms.
Yeah.
Yay!
All right. Thank you guys for watching.
Thank you guys.
All right. I am going to stop sharing and turn it off. See you guys.
See you. Bye.
Yeah.
Bye.